Alright, so now I'm going to develop our second equation, and I get our second equation from block B. I do the exact same thing, but I use the forces of block B and determine the work done on block B, and here it is. So first I need my free body diagram, and I do that by drawing the inclined plane, and block B is at a 30-degree angle. And I don't like to draw my block because too many lines in the free body really start confusing the issue. So I draw my normal, which is perpendicular to the object. So that's the normal of block B, and the normal would extend through, and it goes along the y-axis. Here's my x-axis, positive x here, and so my weight is next. My weight of block B comes straight down. The angle between the weight and the y-axis is 30 degrees. And I'm going to have tension pulling up, and I'm going to have friction going against motion. Again, I've assumed the blocks to kind of go this way. So my friction is going to be that way. And so for my work, I know that it's force times distance, and the force and the distance have to be in the same direction. So this is why I've aligned my axes the way I did. I know that there's only going to be motion in the x direction, so if I can align my forces in the x direction, then all I have to do is multiply the sum of the forces in the x direction times the position in the x direction. And so I'm going to take the sum of my forces here, and I'm going to multiply it by the change in position, and that's going to equal my work. And I need that in order to substitute it back into my work and energy equation. So sum of the forces in the x direction, I'm going to have tension going in the negative x, and I'm going to have friction, positive x, and I'm going to have work in the x direction. I'm going to have the weight in the x direction, WBX. And so that's my force right here. And then my change in position is given in the problem. It's going to move 1 foot, and the direction that I'm choosing is negative x. So it's going to move negative 1 foot, and that's going to equal my work. And once I go through and solve for friction and solve for the weight in the x direction and substitute in, I get 27.165 minus my tension times negative 1 equals my work. And so now that I have my work, I can substitute into my work and energy equation, and that's going to, again, my initial velocity is 0, so the initial term in the work and energy equation goes out. So I'm left with my work is going to equal 1/2 the mass of block B times the final velocity squared of block B. And I know what my work equals, so I have 27.165 minus tension. Again, I have to take note of this negative 1 and change my sign. It's negative 27.165 plus tension, and that's going to equal 1/2 times 1.55, which is my mass, times the final velocity squared. And so now I have my second equation. I can now solve simultaneous equations for tension and final velocity. So now I'm going to solve for tension and final velocity. So I have equation number 1, which is negative t plus 33.585 equals 1.55 over 2 times velocity squared. And in my second equation, I have negative 27.165 plus tension equals 1.55 divided by 2 times velocity squared. So I'd most likely solve one of these for velocity squared, and then substitute that in and solve for t first. But you can go through it any way that you like. Your final answers will be t equals 30.38 pounds, and your final velocity equals plus or minus 2.03 feet per second. And the plus or minus again comes out once you solve for your square root. Whenever you have a square root, it should always be plus or minus. And in this case, once we go back to our diagrams and figure out what direction this block is moving, we see that in both cases, the final velocity of A equals negative 0.203 feet per second in X, and the final velocity of block B equals negative 2.03 feet per second in X. You could also draw that, instead of using a negative sign, you could just use maybe some sort of like an arrow pointing at 30 degrees, and so you'd have 2.03 at 30 degrees, and